All right, so welcome to the first week of the summer 2026 ELNC, ELEC, ELEC 3067, 26 summer electrical machines. All right, so this is the second class that we have this week. First one was in person, and this is the online part. All right, so let's just start. Today we're going to talk about the review and Faraday's law, motor rule, and of course the phone rings. Someone's going to pick it up. Okay. We'll talk about the Faraday's law, motor rule, generator rule, and we're going to kind of wrap it up. And also we'll talk about, during the second presentation, I'll give you the angular velocity concept. All right, so let's start with this one here. That's the review thing here. Electrical power, when we're talking about the RMS value, so the power and the little E subscript here stands for power, electrical power, as opposed to a mechanical power. Just going to quickly check if we're recording. Yes, we are. All right, so mechanical power with the little subscript of the M, power mechanical. Here's the formula, N times T over 9.55, and later on we'll find out where the 9.55 comes from. So for the electrical power, we're just multiplying the voltage and the current in the, that's passing through a load. And if this is an RMS value, then we got the value. As long as we get the RMS values of the voltage and the current across the load. Now, mechanical power, we get the N, and the N stands for speed, and the T stands for torque. All right. And the speed, we're talking about the rotational speed, which is rotations per minute. T stands for torque, and these are the Newton meters, and divided by 955. As long as we know the speed, rotational speed, and the torque, divide that by 9.55, and we get the mechanical power, and that's going to be in watts. And also here the power, the voltage times current, also the power gets in watts. All right, so what does it say? Magician in electrical machines, question mark. Well, magnetic field, that's the magician. That does the job. Two methods of to get the magnetic field. One is the electrical current that we're passing through a coil. And just as a reminder, as a review here, where's my board? Let me get my board. Here is my board. All right, so when we have a conductor that is, let's see, this is a resistor, R, and here is some sort of a power supply here, and let's get a switch. And when we close the switch, we have some sort of a current flowing that is going to go from, let's say, positive to negative. Considering the conventional current flow, we're going to have the current with the designation of I. And of course, when we're using the right-hand rule or the corkscrew analogy, here's the corkscrew here, okay. and when we're turning the corkscrew this way, the corkscrew is moving that way, so this would be the direction of the current, and this would be the direction of the magnetic field. All right. Now, when we have just a single piece of wire, the magnetic field is going to spin this way around the piece of wire. All right. Now, when we coil that wire in such way, like this here, then we're going to create a magnet, or so-called electrical magnet. When we look at the direction of the current flowing and the magnetic field spinning around that, and if we coil it up, those lines are going to add up into something like this right here. Okay. So then we're going to have the North Pole, and we're going to have the South Pole of the magnet that we just have created, and the magnetic field lines that are right inside the coil right here. We are going to call that a magnetic flux, which is the magnetic lines, magnetic lines on the magnetic field that we care about, that is going to do the work for us. Now, things are going to get a little bit more interesting when we insert some sort of a ferric material, like a cylinder inside here, or magnetic core, or ferric core. Then that core is going to make it easier for the magnetic lines to pass through, and of course that thing is going to get magnetized, and we're going to have a magnet here with the North Pole and a South Pole. It's just like having a permanent magnet, but it's not a permanent magnet, it's an electromagnet. It works as long as the current is flowing. Okay, so that's the idea. Or another way to get magnetic field is to have a permanent magnet. Right? Now, just as a review from last time, the magnetic bar that we have, if it's magnetized, it's going to have a North Pole and it's going to have a South Pole. If we cut this in half, we're going to have two of those with North Pole and South Pole each. There is no a monopole that exists that we could find, although theoretically some people tried to prove it, and apparently they did in some sort of way or not, that we could have a single monopole. But for now, we're just going to say that it doesn't exist. Okay. Also, we didn't talk about that yet. Maybe we're going to talk about this next time, the hysteresis. All right. So now when we have that, some sort of a ferric core is going to have a different type of something that's called a permeability, and permeability is the describes to us how easy or how hard it is to magnetize that material. And there is that the hysteresis curve. The way, I'm just going to give you a bit of heads up on how this thing works. This is the magnetic flux density inside that magnetized thing, whatever it is, some kind of a ferric core, which is not magnetized. But once we start running current through the coil, and that thing is going to be inside that coil, it is going to get magnetized when the current flows through the coil. And after it gets magnetized, when we cut off the current, it's supposed to stay demagnetized. However, it doesn't happen that way. With different permeability factor, those are going to be having a little bit more residue or less residue of magnetization. All right, so this is not like, okay, so this right here, this is x-axis and y-axis, and this is not just like the time continuum that goes from left to right. This here, you can treat it as oscillating from left to right, like that. Okay, so when we start from zero, when this whatever the magnetic core is not magnetized, once we start introducing magnetic force or the strength of magnetic field, then the magnetic field is going to be stronger, and that depends on the number of turns and depends on the amount of current that we're passing through. That is going to give us a stronger magnetizing field or magnetizing force, or weaker magnetizing force. Of course, the more turns, stronger magnetizing force, and or the bigger amount of current, greater amount of current, also is going to cause a stronger magnetizing force. So when we increase the magnetizing force, that ferric core is going to magnetize, it's going to get magnetized, and it's going to have that flux density in there, all right? Which is, well, we're going to have certain strength of the magnetic field or the flux density. And then when we start increasing that magnetizing force, we're going to reach something that's called a saturation point, that when we start increasing current or adding turns, that material that's inside is not going to magnetize more. It's just going to say, enough, that's as far as I can, that's as much as I can eat, and I'm not going to get any stronger. So then when we start going back with the strength, it is the magnetization of the how that thing stays magnetized. It's not going to demagnetize down to zero. It's going to have some residue here. Yeah. Now we keep going back. We're going to reverse the magnetic field, and we're going to reach the saturation in the other end, and we're going to go back to zero. That thing is still going to have some magnetization going on. So this is the hysteresis curve. Now, some of the hysteresis curves are going to be wider or narrower, depending on how easily the material or ferric core is magnetizable or not. Right? And that's as far as I'm going to give you that. We're going to take a look at, we're going to dive deeper into that later on. All right, but not much. So two methods of getting magnetic field: electric current or permanent magnet. That's both going to give us magnetic field. What's magnetic field? Well, there are magnetic lines of certain strength that travel in a certain direction. They always travel from north to south. All right. On the outside, of course, in the inside of the coil, then we're going to have another thing happening. Notice that those lines are going to travel from south to north. Inside that, outside, they're going to go from north to south. They're going to try to find a way. Right? Now, of course, if we put, I'm going to get my board here. If we put a couple of permanent, let's say permanent magnetic bars, let's say here, well, I'm just going to draw them. I'm going to draw some new ones here. So if we have two magnetic bars, and they're going to have north and south pole, and if we have another one here, and let's say this one is going to have south and north pole, so this is just like this situation here, okay? Except this is just kind of a diagram that's drawn, showing that maybe there is something that is called a monopole. No, it's not. We just kind of, for the simplicity, we're going to draw it this way, all right? So then, of course, the magnetic flux is going to travel. The magnetic lines are going to have this direction from north to south, just as is shown right here. Okay? But this thing here, this here, is this here. Okay. All right. Oh, what did I do? What did I do? Okay. Back online here. Then we're going to skip this for now. We're not ready for that yet. And, well, okay. Well, maybe we can. All right, so here's the magnetic strength, magnetizing strength, and here is the magnetic flux, or the magnetization, or the strength of the magnetic field, and this would be a curve of behavior of a certain magnetic or ferric, or certain core, certain material, right? So let's take a look at this example here, and we're talking about the saturation of magnetizing. You see here, if we increase, in this case here, if we increase the magnetizing force, the magnetic field is going to get stronger, 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 and then it's going to start leveling off. No matter how much more we give, it is going to, the magnetization is going to level off and stay no more. All right. So let's see what this example gives us. The saturation curve of the coil is given at the right. So this is the here. To achieve 1.2 Teslas of flux density we're measuring in Teslas, the strength of magnetic field. What is required to magnetize what is the required magnetizing force? From x-axis we can find that right, where's the 1.5 Teslas? Somewhere here. 1.2 is about here. 1.2, right? Then we just draw a line here. Boom. In this case, we need about 1100 amp meters, because magnetization strength, or magnetizing force, the unit is amperes and meters. The meters of what? The meters of it's not the length of the wire, although sometimes it coincides with that. However, this is the length of the magnetic field line, which would be something like from here to here. All right. All right, so what we have, the magnetizing electrical and magnetic field. Direction, the right-hand rule. Yeah, the right-hand rule when we're talking about, where's my board? When you see that wire here, if you have your thumb here, that would be the direction of the current, and then when you wrap around your fingers here, and that would be your hand. All right, so this would be the right hand rule. The fingers wrapping around the conductor would show you the direction of the magnetic field spinning around this this conductor, and this would be the direction of the current. And of course, when you coil that up, you're going to get this effect, because those lines are going to add. So that's what it means. We're using the right hand rule. All right, so flux density we're designating with a letter of B, and we are measuring that thing in Teslas. Now here is the permeability, Teslas per amp. Okay. Maybe I should give you another short lesson. We're going to squeeze that in somewhere on the concept of permeability. And permeability talks about is the quality of how easy it is. It tells us how easy it is to magnetize or demagnetize something. All right, like a ferric core, usually. Right? Ferric stands for ironic, not ironic from irony, but ironic from iron. I think I just made up a word. So ferric stands for iron core, right? Then there's that N stands for number of turns over here that we are using and how much current we're passing through. Let's take a look at this example here. 10 amps right here is fed into a coil that has 100 turns. The permeability of the of that core is 1.5 times 10 to minus 3, right? Teslas per amp. What is the flux density inside the coil? All right, we have that thing pretty much laid out for us here. So when we apply this this formula right here, we're going to come up with the flux density of 1.5 Teslas. All right. Yeah, once you download this thing, you can just take a second look at that here, right? All right. We took a look at the hysteresis curve and and the magnetizing example here. All right, so okay, that was the lesson that we had. All right, now, there it is. Faraday's law. Let's take a look at that here. Changing flux in a coil induces voltage. All right, so let's say we have a coil. This is just, oops, I tried to draw here, but I can't. This is the coil that has many turns, however amount of turns that is. And we're not going to hang up on the polarities yet, because that's another topic. Let's say here's a plus and here's a minus here, and then this would be the magnetic field. So that tells us this would be north and this would be south, right? And there's an n amount of turns, and well, it's on this picture. It shows frequency. We're not going to talk about that yet. Well, frequency, the field is changing with certain frequencies. Sometimes that's the idea here, right? But we're just talking about one kind of like one shot of change, all right? So ignore that frequency word right here, the frequency quantity here. All right. So in order for voltage to be induced in the coil, the magnetic field has to change. Right? So if there is certain strength of magnetic field that is cutting through the core of this coil, if the magnetic field stays constant, then there's going to be no voltage induced around those two ends of the coil. As soon as the magnetic field changes, then the voltage is going to appear. So when we have the magnetic the magnetic flux changing over time, then we're going to have a voltage induced. Now, this magnetic field can go one way or it can go the other way. Depending on which way it goes, we're going to end up with a plus and minus here or minus and plus here. As long as the magnetic field changes, at the moment of change, then the voltage is induced. If we shove in a permanent magnet right there, at the moment of pushing and moving that magnet inside, there's going to be voltage induced. Once we put that in and stop halfway, then the voltage is going to disappear. Right? So that's the idea here. So changing flux in a coil, that's one spin on Faraday's law. Changing flux in a coil will induce voltage. So that's the Faraday's law of electromagnetic induction. Right? All right, continuing on that, the voltage, and over here, okay, so sometimes you're going to see a little minus sign on that. We're going to talk about that later. But let's just talk about the absolute value of this thing right now. All right. So we have the induced voltage right here, and then we have the number of turns, depending on number of turns. So more turns in the coil, there's going to be more voltage induced. And here's the delta flux. All right. There's that Greek letter phi for flux. That delta represents change. So change of the magnetic field over time is going to induce voltage. And the more turns we have, the more voltage we're going to have. The more change we're going to have, then the more voltage we're going to induce across here. And because the delta time, or the change in time, is on the bottom of the equation, so the shorter time it's going to take, the more voltage is going to be induced. Well, it makes sense, because over the shorter time means we're going to change that magnetic field faster, so more aggressive, or more aggressively. Then, of course, we're going to induce more voltage at that moment. All right. So the letter E stands for induced voltage, and it's in volts. And number of turns, it has no unit. It's just a number. How many turns? Change of flux. Delta represents change of flux, and that's in Webers. Sometimes you're going to hear Webers, and sometimes Webers. Okay, so depending on where you are, you're going to hear that. Okay, now then it's change of time, and the time we are having in seconds. And here's another example right here. A coil has 2,000 turns. A coil surrounds a flux of 5 milliwebers. Flux of 5 milliwebers produced by a permanent magnet. Okay, the magnet is suddenly withdrawn, causing the flux inside the coil to drop to 2 milliwebers in 0.1 second. What is the voltage induced? Apply this formula here, and we're going to end up with 60 volts. All right, and here's the picture of withdrawing that permanent magnet there. So, all right, at the moment of withdrawal, when the motion happens, that is going to have, of course, if it's removed with a constant speed, we're going to get something like a sine wave type of a peak at 60 volts. All right, the motor rule. What's happening with the motors? Lorentz force. All right, electromagnetic force. Conductor carrying current. So now we have the scenario of, magnetic field that goes from north to south right here. And we have a conductor in which current flows. So when we have that, when we induce current, that thing is going to have tendencies to move. Where is it going to move? Left or right? Well, left-hand rule is applied here. When we put our hand into that system, that our left hand, in a way that the field is going to hit our palm of our hand. So that's going to be our thumb right here. That thing is going to have tendencies to move. Now, here's another perspective on that. So basically, that's looking straight into it. And there's a little X, which means that the current is flowing into that conductor. And if we had the dot, that would be current flowing towards us. Just imagine an arrow. This would be the fletchers of the arrow. If the arrow is flying away from you, you're going to see this. And if the arrow is flying towards you, you're just going to see the tip of the arrow, which is going to look like a dot. All right, so that's what that X means here. How does this thing work? Let me get my board here. All right, I'm just going to let me get this one here. Make it bigger and shove this aside. All right, so let's see here. There's a conductor and there's a current flowing into the conductor. So the let me just change the color of my marker here. All right, so using the right-hand rule, wrap around things, the magnetic field is going to spin this way here around the conductor. So it's going to spin that way right here. All right. Let's see here. Make it a little bit so you could see it better. All right. Now, when you have those magnetic lines cutting across, those magnetic fields on that side are going to add with the direction of the magnetic field spinning. Okay. And over here they're going to oppose. This thing is going to be having more energy at this time. At this side, it's going to have less energy, and so it's going to be pushed that way here. Okay. So there, it just keeps running away on me. All right, where are we here? Here. Okay, so we're looking at left-hand rule. If this is the direction of the current flowing inside the conductor and the magnetic lines are cutting through across here, that conductor, that physical conductor, is going to have physical tendency to be pushed that way. Right? Lorentz force. Conductor carrying current, magnetic field force, direction, left-hand rule. Yeah, perpendicular to the... no. Yeah, okay. There's some letters here. Okay, Lorentz force. Force equals flux density, strength in Teslas, times the length of the, well, that would be length of the conductor in this case here, and the amount of current that flows through. Let's see the example here. Conductor 3 meters long here, carrying a current of 200 amps is placed in a magnetic field of 5 Teslas. Calculate the force on the conductor. If it is perpendicular, if the force is perpendicular to the current flow, right? So we have an ideal situation here. So we are given the length is 3 meters, the current is 200 amps, the field is half a Tesla. All right, apply this formula, and we're going to have the force in which this thing is going to be pushed of 300 newtons. That's about 30 kilograms or 60 pounds. Here, right? So here's the example. All right, now let's see the generator rule. All right, there's a little bit, okay, here. Generated induced voltage. We're going to induce a voltage now inside that this conductor here. All right, so now we're talking about the generator. What's happening at the generator? So instead of having a stationary conductor and running current through it and see what happens, then we're having the conductor. We're going to move it in and see what happens, how we're going to generate a voltage inside the conductor. Now, here's something that we really have to understand. Let me just create a new file here, new page. All right, so when we have a battery, okay, here's the positive side, negative side of the battery, and we have a circuit, and we have a load in terms of resistor. Considering conventional current flow, we're going to have the current flow this way here. All right. So we're going to have the current flowing this way, current flowing this way. Now, because this is positive side, positive terminal of the battery, this is negative terminal of the battery, then when we run the current through the resistor, there is going to be more positive side of the resistor or the load, or more negative side of the resistor at this point here. So the current flows. The current keeps flowing, and the current keeps flowing, right? And the current keeps flowing. What is happening here? In the power supply, inside this power supply, the current flows from negative to the positive. So if it's a electromotive force, which is the force that powers up this whole system, the current inside that EMF, electromotive force, the current flows from negative to positive. When we move across the load, here's obviously this is more positive side of the load, this is more negative side of the load. The current flows from positive to negative. That's the concept that we have to understand. Now, when we are running the conductor inside magnetic field, all right, so here are the lines, they're going this way. All right. Now we're going to run a conductor, we're going to shove that in, this conductor, all right, is going to go this way here physically. All right. Then once it's in motion, it finds itself cutting through those lines. So that's going to be the magnet, that's going to be the rod. All right. We're going to create a power supply out of that rod. So how is that going to polarize? All right. How is that going to polarize right now? It's going to polarize so the current flows from the negative to the positive. Here, here. We're going to have a current flow here. I hope I draw this thing right. I'll have to analyze it further. Maybe we're going to have a few minutes so I could do that. Because that thing is going to oppose. How is that going to oppose? See if I did this thing right. All right. When this thing is in the motion here, so it's moving this way, so this side of this conductor, if you magnify it, is going to be hit with the change of magnetic field that's going from this point to this point right here. From here to here. It's going to have in this direction. And that thing is going to oppose that. So it is going to create an opposing force. All right. And if we use the right-hand rule or the corkscrew, we're going to have the current flowing this way. All right. Like the arrow here. And the current's going to flow this way here. And because it's the power supply that we made out of it, so it's going to be negative here and positive here, if that's the road. Okay. So if we connect a resistor to it, or a load, the current is going to flow this way here. Because on the outside of the power supply, it goes from positive to negative, and on the inside of the power supply, it goes from negative to positive. All right. Now, where am I with this thing here? Good. All right, so here is, we're doing right-hand rule here. So if we place our hand so the lines are hitting our palm of our hand, then our fingers are going to point towards the electric current flowing. And you see here, here's the electric current here flowing this way from negative to positive. And this is the small letter E, because that's what we're creating EMF inside that rod. We're making a power supply out of that. So the current is flowing this way, okay? This way. And so if we have open hand with the fingers pointing towards the current flow, and the magnetic field is hitting our palm of our hand, then our thumb is going to point towards that thing moving. But this is not an induced movement. We are moving it physically and creating the current flow in that. Okay? So that's the generator rule, or the generator concept. So we can, the idea here is that we can generate voltage by moving the conductor in there, or we can create movement by physical movement of the conductor by introducing voltage to it. Okay. Induced voltage, E here. What do we have for example here? Equals B, which stands for the flux density, strength of the magnetic field that's cutting across the area that we care. Then the length of the rod and the velocity here. And you see we're dealing with the linear velocity, which is that going straight across. Like that, linear velocity as opposed to angular velocity. Okay. And if we know the strength of the field, we know the length of the conductor, and we know the velocity, linear velocity, then we can predict or calculate whatever the voltage. So if we have, what do we have here? We have 2 meters long rod. The strength of the field is 0.6 Teslas. And the movement of that is 100 meters per second. That's quite fast. Right? Calculate the voltage that is going to be induced. Well, if you apply this formula here, we're going to get 120 volts appearing across that, and that is the way going to be appearing. All right. Summary. Well, Faraday's law, so the induced voltage, so the force, here's the voltage formula, here's the force formula, and here's the EMF. Okay. Now, in this case here, right here, how can we make this rod longer without making the whole thing bigger? We can just add more turns. Then more length of the wire is going to be exposed to the field, to the magnetic field. So, if we are dealing with a single rod, here is the formula that we're going to apply. But if we have 2 turns, or 2 of those, then we're going to have a little letter N before that, that would symbolize that would stand for the number of turns. Because if we have 2 of those, then we're going to have 2 of those. We have 3 of those wires, we're going to have 3. So that N is going to represent that. And we're talking about absolute value here right now. But just so you know, so there is that polarity we're doing it. So that's going to be a minus N BLV or minus BLV. Because it's a power supply that we have created here. Now, I want to give you one more thing. That's not over yet. We're not over yet, all right? I want to give you the concept of angular velocity. And let's see here. We're going to have that. All right. Angular velocity. What is the angular velocity? Because we have linear velocity and angular velocity. All right, so the angular velocity is the rate. Okay, let's see the definition here. It's the rate at which an object rotates or revolves around a fixed axis here. So angular velocity is telling us how fast something spins. And the linear velocity tells us how fast it's traveling across in a straight line. All right, so linear velocity, how far an object travels in a straight line. Angular velocity, how much of a turn it makes at a given time. And the angular velocity we're representing with the letter omega, Greek letter omega, small letter omega. And it's a vector force because it's got a magnitude and it does have a direction. All right. So also we are talking about the unit here. The standard SI unit for the angular velocity is radians per second. So omega equals radians per second, or sometimes you're going to see something like this. Radians times second to the negative 1. It's the same thing, right? Now, just a quick reminder, what is a quick review, what's a radian? A radian is a unit of angle measure based on the radius of a circle. So here's the radius of the circle. And if we take that and if we lay it on the arc of the circle, that angle is going to be 1 radian. If we draw a line, so that is going to be our radian here. 1 radian. Without making the story too long, 2 pi is the whole circumference. So 1 radian equals 180 degrees over pi. Approximately 57.3 degrees if you want to do that. So if you have the radius, lay it out here, you're going to have an angle of approximately 57.3 degrees. Pi radians, so 3.14 goes to no end, times a radian equals 180 degrees. So the angle, well, if you go here, you're going to have radians, the radius times pi. So 2 radians is a full circle. 2 pi radians, sorry. 2 pi radians. Right? A radian is a standard unit for an angular measurement. You can get the angles in degrees, or you can get the angle theta in radians. All right, so calculating the angular velocity. To calculate the angular velocity, omega, divide the change in angle, delta theta, in radians by the time it took to change in seconds. All right? To convert from RPM, rotations per minute, to radians per second, you just multiply the RPMs by 2 pi over 60, because minute has 60 seconds. Right? Revisit this, look at that until it hits you. Now, angular velocity versus linear velocity. Angular velocity, it's the rotations per time, which would be how many radians per time. So how much is that angle going to change in radians per given time? So that's the rate at which something spins around, how fast it spins. And linear velocity is if you draw a tangent on it, on the circle, at that one point in that microscopic of a microscopic of a microscopic second, that thing here, that one point on the circle, is going to have a velocity that you could compare to going in a straight line that way. But you blink and it's not there anymore. It's at one point, another point. Right? So sometimes we're going to need to know what the angular velocity is, how fast it spins, and you can have rotations per minute, or you could have radians per second. And sometimes we're going to be interested in, at that moment, what would be the momentary linear velocity of that point. So the linear velocity, small letter v, is whatever the distance is, here, the arc, over the time. So we're talking about the distance here that it covers, because if you straighten it out, you can straighten it out and calculate the distance, or you can just measure the distance of that line here per time. So the linear velocity, the distance it travels per time, and the angular velocity, omega here, it's how much angle it cuts through over time. Linear velocity is also known as tangential or tangential velocity, because if you have a tangent, you just draw on it, and that would be the linear velocity at that moment, at this point of the circle. Direction and the right-hand rule. Direction of what? Of the angular velocity. Right-hand rule here. Spinning direction, and there's the magnitude of the vector. So the direction, if it's counterclockwise, then we are having a positive angular velocity. If something spins clockwise, we're talking about a negative angular velocity. Couple of problems here. An angular velocity practice problems. All right, let's see here. I just got some stuff from the internet that I found pretty interesting here. And here's the references. Question 1. Calculate the angular velocity of a 0.5 meter radius bus tire. When the bus travels at 10 meters per second, which is about 36 kilometers per second. Solution. We have the velocity of 10 meters per second, so that will be the tangential, or the linear velocity here. And here's the radius. We know that. Here's the formula. Velocity equals radius times angular speed, or the angular velocity. If you just derive that formula from here, flip things around, you're going to have the angular velocity. That is going to be the linear velocity divided by the radius. It's okay, we can catch that. If you have to leave, that's fine. You can catch the rest of it when I post it on YouTube, which is going to be later tonight. Yeah. Thank you for showing up. All right. So simple calculation, and you see here, you get 20 radians per second. You see sometimes you're going to see something like that. I was going to change it, but I said, no, I'm going to leave it. Because if you see something like this, that means 20 radians per second, or 20 radians times second to the negative 1. That's basically what it says here. Another problem here, a car wheel of a radius 20 inches rotates at 8 revolutions per second. Oh, that's getting complicated here. On the highway, what is the angular velocity of the tire? Solution. The following equation gives angular velocity. All right, here, omega equals angle per time in radians. Since the car has completed 8 revolutions per second, we multiply by 2 pi. Since a full rotation is 360 degrees, so that equals 2 pi. Yeah, that's fine, Nico. Thank you. Where are we? Here. Now, substituting the values in the equation, 16 pi radians over 1 second. We got 16 pi radians per second. So here is the angular velocity of that. Here's the answer here. Look at it until it hits you. As I said, sometimes you will see the unit expressed this way. Again, 16 pi radians per second. 16 pi radians times second to the negative 1, which means 16 pi radians per second. Now, here's an interesting problem. That's one of those things that we had it in the first class. I got 2 approaches, approach 1 and approach 2, okay? All right. A wind turbine drives a DC generator at 340 RPMs, rotations per minute, with the force of, or the torque of 5.8 Newton meters. The generator charges a battery of 13.8 volts with 11.6 amps. What is the input power of the generator? The input power of the generator, we're talking about mechanical input, because a generator turns mechanical power into electrical power. Okay? So, the input power, we're going to know that this is a mechanical power because we're generating electricity. All right, so let's identify the input parameters. A generator system, the input power is the mechanical power delivered to the shaft by the wind turbine, we use the given torque and rotational speed for calculation. So the torque that we have is 5.8 Newton meters. Rotational speed is 340 RPMs. Convert the speed to angular velocity. So we're going to convert that speed into angular velocity, and that is the speed. The end thing here stands for speed times 2 pi over 60, because that gives us a full rotation here. 2 pi radians over 60 seconds. Rotations per minute. See that? Rotations per minute. How many rotations per 60 seconds? Okay. So then the angular velocity, we have approximately, we are plugging the numbers, we're going to have 35.6047 radians per second. All right, so we have that angular velocity. And the mechanical power is simple here now. The power equals to the torque. See? Torque times angular velocity. That's why we have to get the angular velocity from the RPMs. So so when we have when we want to convert from rotations for RPMs, rotations per minute, into angular velocity, we just get the rotations per minute and multiply it by 2 pi over 60. Again, how many rotations per minute? This is a minute. 60 seconds is a minute. So how many, again, rotations, full rotations, 2 pi radians per 60 seconds. All right? Rotations, how many rotations per minute or 60 seconds? So then the formula is simple here. We've got power, input power, which is the mechanical power, is the torque times the angular velocity, and we come up with 206 51. See here, I put that here, watts. So this is using the angular velocity. Also, we have another formula here. Same question here, different approach, using different formula. All right. You see here, that's where the 9.55 comes from in that formula that we're using in earlier lesson here. Torque times speed, or speed times torque, divided by 9.55. The 9.55 is 60 divided by 2 pi. But because we're taking it from the numerator to the denominator, we have to flip that 60 and 2 pi over. Okay. So the torque is 5.8 Newton meters. The rotational speed, and that's that's in RPMs and Newton meters. The units have to be what they have to be. This only works when we have RPMs and torque in Newton meters. So we have to make sure. Okay. So we are applying the formula: torque times speed over 9.55. Torque we have in Newton meters, check. Speed we have in RPMs, check. Divided by 9.55. Plug in the numbers. Divide this by that. What do we get? 206.51 watts. Same question here. We have to have the same answer. All right? 206.51 watts. Approach 1, again, 206.51 watts. So there's more than one way to skin this cat. All right? All right, so I'm talking here to myself. I have to get going. Thank you, thank you. All right, so that's it for today, and I'm pretty sure you're going to be able to catch this thing on YouTube. And tomorrow we're going to see each other in the lab, and next week we're going to have next in-person class, and then again online class. Thank you, and have a wonderful week.